Okay, we start the second lecture now on this 100 years of quantum mechanics at IMSC, and the talk is by Professor Shankar, professor from this institute, who has been associated for several decades, who also happens to be, I happen to be his friend for at least some 4.5 decades. And as a student, I knew him, and as postdoc and as a faculty friend, more or less around with me at that time, 90s. And we have been associated also on several issues. And he will talk to us about fractional statistics. So he did his PhD from Tata Institute of Fundamental Research. And then he was a postdoc here in the 80s. And also at later at IIT Kanpur, he was there. Then he joined along in 91, if I'm right, and IMSC here. And he is an expert in low dimensional quantum field theory, condensed matter physics. Now after that, he also moved into glacier physics and various activities. Tsunami, various things, and he has a lot of interest in several activities. He has been very helpful to me in popularizing science in several places. So now I'll give it to you, Franz. Go ahead.
Is that better? Okay. So let's start from the very beginning. So this is why we are here today. These are the two papers, one by Heisenberg in 1925 and the other by Schrodinger in 1926, which is what we consider laid out the foundation of quantum mechanics as we use it today. There were about 2 decades of work preceding this papers, of course, but that's why 100 years from that time we are celebrating. So of course, both these papers discuss single particle quantum mechanics. Heisenberg in terms of the operators and matrices picture, Schrodinger in terms of the wave function. But then the experiments from which quantum theory emerged were all many particle systems. Black body radiation, which is a many photon system, and atomic spectroscopy, which is a many electron system. So obviously people were thinking about many particle quantum mechanics even as this was developed. So 2 sort of concepts emerged. One is indistinguishability of identical particles, and the other is quantum entanglement, when you go from one particle to many particle quantum mechanics. I'll be focusing on the first one today. So Bose realized actually that he had to take photons to be indistinguishable in order to produce his reproduce the Planck's law. So that was a paper published, famous paper published in 24. And then Einstein postulated that maybe this is true for atoms and molecules also, and extended the work to bosons. But at that time, I don't think there were any. Helium must have been there, but I don't know what experiments were being done, etc. So people did not realize fermion bosons separately very clearly.
very soon.
Yes, because
They experimented. No, he said that post-Einstein condensation is taking place in liquid helium-4. That's a superfluid. That's the famous work of London. Very soon, but not.
so it got clarified. Just wait for the next slide.
Yeah. Okay.
So then Pauli realized that electrons are different from photons, and they, firstly they have an intrinsic spin, which is equal to half, and they obey a Pauli exclusion principle, which is, so you can't put two electrons in the same state, whereas in Bose's counting, he could put as many as photons as he liked in the same box. Yeah, so things move very quickly. So this is the paper by Dirac, where he sort of puts together Heisenberg and Schrödinger work. And he also discusses the issue of indistinguishable particles, identical particles being indistinguishable, in particular for electrons being indistinguishable. So here is this section 3 is where he goes on to discuss many particle systems. So here the problem is when there are several similar particles. If the positions of two particles are interchanged, the new state of the atom is physically indistinguishable from the original one. Just makes the statement, and then of course he goes on to say what happens to the wave functions. He realizes that the wave functions can be realized in two ways, antisymmetric and symmetric wave functions. But I would like to motivate indistinguishability in the following way. Let's ask the question, why are classical particles, identical classical particles distinguished? Identical means all properties same. So how do we distinguish them? We distinguish them by their initial positions. So over here, if I call this number 1, number 2, then this is number 1 and this is number 2, because this has gone here and this has gone here. But this makes sense only if the trajectory is well defined. But because of the uncertainty principle, quantum particles' trajectory is not very well defined. So you can't say where it came from. So that's the motivation that, that you should have a principle like indistinguishability in quantum mechanics, even though it's not there in classical mechanics. However, it's a principle, not far from a proof. So proof is in the fact that it works, the formalism works. Okay, so here in that same paper, Dirac has written down the general many-body Bose wave functions, symmetric functions. He's also realized that the fermionic many-particle state can be put in the form of a determinant, though we call it Slater's determinant, but I think maybe Slater determinant refers to the Fermi sea in solids. So determinantal form we had already written it. Then he's also derived both the Fermi-derived distribution and the Bose-Einstein distribution for the one's case with symmetric particles and antisymmetric. So, and this is Fermi's paper. Where you can, everything is Italian, but you can recognize this formula. Is the Bose-Einstein distribution. And he was actually interested in explaining a lot of puzzles in this classical theory of metals, the Drude model. And one particular thing was this linear dependence of specific heat on temperature, which he has derived in this thing. So anyway, so by 1926, everything was known. That, in the, what do you call it, that the indistinguishability principle said that observables should be symmetric functions of positions and momenta. Then the mod square of the wave function should be symmetric under permutations. So wave functions, one way of understanding it forms a representation of the permutation group, which has only two 1D representations, either fully symmetric or fully antisymmetric. And so those correspond to bosons and fermions. Permutation group also has higher dimensional representations. Those led to the concept of parastatistics, but those have not been physically realized so far, so I won't be discussing them later. So I guess maybe London's thing came just after this. Well, 30, I think. Then after quantum field theory came about, there is this connect spin statistics theorem, which showed that half odd integral spins are fermions and integral spins are bosons. So this was within the framework of a Lorentz invariant CPT invariant theory. Later on it was realized that Lorentz invariance is not so important. CPT invariance is the important thing. So even quasi-particles in condensed matter can be expected to follow this theorem, provided the thing is CPT invariant. So there used to be in low dimensional sigma models with topological terms about used to have connections between spin and statistics. So those days speakers used to pull out their belts, twist it to show that rotation and particle exchange are the same. So those days wearing pajamas was a distinct disadvantage. One couldn't do such things. But a lot of speakers used to do it, take out their belts. Okay. Anyway, 50 years later came this paper by Linnaeus and Miriam. I don't know how it's pronounced, the name, which showed that d equal to 1 and 2 are qualitatively different. So, and as I say, finally, in 1 and 2 dimensions, a continuum of positive intermediate cases connects boson and fermion cases, and so they discussed that. So how they argued was that firstly they realized, they characterized the configuration space of hardcore many particle systems. So n particles and which can't fit on each other. So that characterization is, so suppose for two particles, x1, x2 and x2, x1 are the same point. You don't know distinction, and xx does not belong to the point. That is when the particles are sitting on top of each other. Now, this configuration space has a non-trivial topology. In particular, it has a non-trivial fundamental group, pi 1 group. Now, for d equal to 3, there are only two classes of closed loops in the configuration space. And so the fundamental group is Z2 and two representative realizations of the fermions and the bosons. For d equal to 2, there are infinite number of closed loops which cannot be smoothly defined to each other. And the corresponding group is called the braid group. Sorry? Yes. Oh, sorry. Yes, Sn.
And the one-dimensional representation.
Sorry, I stand corrected. Yes, that's right. And so this is a braid group with n strands. For n equal to 2 particles, it's an abelian group simply equal to the group of integers. But for n equal to 3 upwards, it's a non-abelian group. D equal to 1, I didn't have time to understand it. It's not a big, there's nothing much to understand there. The point is that hardcore particles are a problem in 1D. Non-interacting hardcore particles you cannot I mean, you cannot exchange two particles without them crossing each other position. So it becomes difficult to, you call it an exchange phase or you call it a scattering phase. There's a sort of ambiguity there. So, but I did not have time to properly formulate it, so that's you have a circle, that's true. Yeah. So, in this paper they realized, I mean, so here, in d equal to 2, two particles you can exchange, but as they exchange, they can go around each other. And so the exchange process is characterized by the number of times they move around each other. And when they move around each other, two such points cannot be, two such paths cannot be deformed into each other if you don't allow the paths to cross. I mean, so for example, you could, if you allowed the paths to cross, you would, but if you don't allow the paths to cross, you so they, yeah, okay, I think I missed this slide. Yeah, okay, maybe. So now consider such a, I mean, how this kind of topology affects the quantum system. And this is a classic example of Aharonov system of a particle on a circle. So the physical, since theta is an angle on a circle, the physical condition is that psi naught square should be equal to psi theta plus 2 pi naught square. Theta and theta plus 2 pi are the same point. And therefore, you can have a family of boundary conditions where you pick up a phase at each rotation. If you want to picture a physical system where such a phase can arise, consider a magnetic flux piercing through the circle and consider the particle to be charged. So then when it goes around, it will pick up. Now, these are inequivalent wave functions in the sense that you cannot linearly superpose two wave functions with different omega. Because suppose you try to do that, take this linear combination, then what comes back after a 2 pi rotation is not the same state. So this physical condition is violated when you do this. So these are all distinct, so this is called super selection rule. That super selection, the sense terminology came from selection rules prevented transitions between states with, when symmetry was not permitted it. This one prevents you from even superposing two states. Another common example that we have is you cannot superpose a spin half and a spin zero particle state, because again the physical principle is that it should be invariant under rotation. At most pick up a phase. Whereas if you rotate such a leading superposition, you get a minus sign, you get a totally different state. So these states are not allowed, are not physically consistent. Yeah. Sorry?
If you have a qubit and a qubit, so will that be okay?
Qubit and a qubit. What's a qubit? Sorry?
3-level system. Yeah. Spin 1 and spin half.
No, so 3-level, 2-level doesn't matter.
Okay.
But what matters is how rotation is implemented there.
But we can create superposition of those two.
Yes, yes. No. So it's not a, see, mathematically this is also valid.
Mm-hmm.
Here it becomes unphysical if rotation is being identified with physical rotation.
Okay. Mm-hmm.
And so then the problem is that this condition, this is a physical condition. If this SU2 operator stood for some other operation, not rotation, then it wouldn't matter. So this is the general formalism for so-called inequivalent quantizations. But suppose you have a configuration space with non-trivial topology that is considered the group of all loops in configuration space. Composition law of these two loops is simply that you go through one and then you go through the other. Resulting root is the composition of the first loop and the other loop. And under this composition law, the equivalence class of topologically different curves will form a group. That is called the fundamental group. Now, the family of inequivalent Hilbert spaces are defined by boundary conditions. But so suppose x at 0 to x at 1 is a loop. Then you can x at 0 is equal to some u times x at x, where u is a representation of this fundamental group. So that defines your many classes and what do you call it? So that's a general formalism. So anions are a manifestation of this inequivalent parameter, which parameterizes the group. So I don't know if I've got this algebra right, but what this is supposed to tell you is that if x3 is x1 composition x2, you go through x1 first, then go through x2. So this was their main contribution. They didn't talk about non-abelian realizations, etc. They talked only about abelian representation, and they sort of said explicitly that you can have intermediate between bosons and fermions in 2D. Then came this paper by Wilczek. So this was a paper where the term anion was coined. It's very interesting. So he's written one paper in January 82. So here he talks about this charge flux composite. Imagine a charged particle to which a flux is attached. Then he realizes that the angular momentum of this can be fractional. And then he also says that, statistics also should be unusual, but he doesn't say here that you can have fractional statistics. Then someone must have pointed him out towards this Linnaeus and Mersenne, my guess, because immediately after that he writes the same, he realizes that what he has is a mathematical model of anions as a flux charge composite. So that is this. So he is saying that, I just did, and based on his previous work of properties of a flux charge composite. And the interesting thing is that he's going the other way around. He has a fractional spin, and therefore he says that these things might have fractional statistics. Anyway, so here is where the anion word came about. So then physical realizations in the 80s, there were two major discoveries. One was discovery of the quantum Hall effect and the fractional quantum Hall effect, and the other the discovery of high TC superconductors. So both of them led to anions eventually. Fractional quantum Hall effect very directly, in the sense that very soon after the experimental discovery, the theory also came. Initially there was this theory, Luffin's theory, which explained one class of observed fractions, and then Jayanendra Jain's theory, which was much more comprehensive and described a much larger class of fractions. Both these predict quasiparticles with fractional charge, spin and statistics. What exact number of charge, etc., depend on which fraction of the SQH. But it's there in both. Now, statistics is very difficult to observe in a condensed matter system. I mean, you can't exchange two particles and see the phase it picks up. But fractional charges have been now routinely observed in a large number of fractions. So this in particular is special because this is supposed to be a non-abelian anion. 1/5, 1/3. So these are all the shock noise experiments. So you look at the noise in the current, and that gives you, in a fairly model independent way, the unit of charge of the current carriers. Most of these are these tables. So in high TC, not directly, but high TC led to there's Anderson's RVB theory of high TC, where he said it's appropriate to look upon high TC materials as doped spin liquids. Doped. So anyway, there was a lot of interest in frustrated antiferromagnets after that time, and and this concept of a spin liquid. Spin system which remains paramagnetic even at zero temperatures. So this led to the idea of a spin-on, but a spin-half excitation in antiferromagnet. So in the paramagnetic phase, there's no spin, and there's an emergence of spin-half excitation. So this paper by Bhaskar and Anderson gave a very interesting way to view it. So there were all these things of emergent gauge fields in these systems. You could classify it as in a gauge theory. And the idea was if the gauge theory is in the deconfined, so the picture in high TC thing was there's an electron and there's a spin-on, and they are bound together by a gauge field. If the gauge field is realized in the deconfined phase, these two are free, and you see the spin-on independently. If it is realized in a confined phase, then it becomes like an electron. So this paper had a big influence on me because end of my PhD, Bhaskar came and talked about it in TIFR where I was doing my PhD, and that was one of my main motivations to shift to condensed matter. Shift to condensed matter and come to math science. So later on it was shown that actually the gauge group was not exactly right. U1 gauge theories didn't have the correct phase diagram, but Z2 gauge theories did have it, and the concept held. And this is a remarkable paper which then gave a user-friendly, exactly solvable two-dimensional model where all the spin-on was explicitly realized. And spin liquids also have now been experimentally seen in various systems, so they well accepted that they exist. So next came another concept of this generalized exclusion principle. So this is, I'll just go through this paper soon. So firstly, it is generalizing, in this paper, instead of talking about exchange phases of wave functions, etc., he generalized the exclusion principle and defined a bunch of exclusion principles which could interpolate between bosons, fermions, and go further also. But however, like he said, this new definition does not apply to anion gas. And Murthy and I solved this problem. It's one book that I'm quite proud of, so that's a big boldface font over here. So how his concept was like this, that now consider a system which n one-particle states. Now, if you put one particle in one of these boxes or one of these states, then how many states are left for you to put the second particle? So in case of a boson, there are still d states left. Because basically if you have 3 states, you put one boson here. Second guy also you can put in any one of these 3. Third guy also you can put in any one of these. Whereas for fermion, because of the exclusion principle, once you put one here, then number of states left for you are only 2. So when n is 0, number of states is 3. When n is equal to 1, number of states is 2, and so on. And at some point of time you can't put in any. So that is what he generalized. Here firstly he is just giving the context, just saying that these are for quasi-particles in condensed matter systems, and these are not for fundamental constituents of the matter. Then he defines this. So this alpha, so the change in the single particle dimension when there is a change in the number of particles you put. Now forget all this alpha, beta, because here we are just considering a general case of many species, many types of species. But this is just delta D, the change in the available 1D space is some G times change in number of particles. Now this G can be anything. Nobody says it should be 1 or 2. So it could be that you just put in one particle and all 3 states are excluded. Imagine a very strongly repulsive system or something like that. And also when you put in one particle, maybe 2.5 states are left. 2.5 states means you put in 2 particles and that cuts out only 1 state. When you put in one particle, the remaining 3 states, when you put in 2 particles, only 2. So this generalizes. And then he gave examples. He applied it to specific systems. For example, SQHE particles, where he showed that actually this exchange statistics number is the same as the phase picked up. The statistics defined in terms of wave functions and the symmetry property of wave functions is the same as the statistics of his definition. He also gave the example of a spin-on in a 1D system where he shows that the G for a spin-on is half, so you should look at it as a semyon in Brownian language. Yeah, so these are just saying that this can be applied to Laughlin quasi-particles, it can be applied to spin-ons, it cannot be applied to gas. Yes, sorry, that's an important thing. But this concept is independent of dimension. There is no topology of configuration space, nothing is coming into this. So it can happen in 3 dimensions, it can happen in any number of, it in principle can be realized in any number of dimensions. So then the other thing was non-abelian anions in FQHE systems. This idea of using them for quantum computation was probably first set forth in this paper, but this is the one that's quoted for it. So the idea here is that qubits need to be very stable in the sense that the 2 energies, the 2 states that represent the qubit, their energies have to be exactly equal. Otherwise, the information stored in it will decay in time. Only if this epsilon is, delta is 0, then this qubit will remain in the same superposition, otherwise it will decay in time. And the gate operations that you do have to be also very precise. Now, so the idea of using non-abelian anions for this is that firstly the degeneracy is actually guaranteed by topology, and I'll come to it in a later this thing. And also the gate operation is that once you braid two of these anions around each other, you come back to a new state, new rotated state, so that's the gate operation. Now it's very robust against how you braid it. Whatever mechanism you use, even if you make small, once you do it this way, second time you do it this way, it doesn't matter. You always get the same state back. So that's the whole, in physics, topology means robustness. Robustness against perturbations, and these things are robust against perturbations. Yes. Yes. Yes, no, so, yes, okay. I never wrote explicitly, is it? So, for anions, very explicitly equal to V to power I alpha. For abelian anions. Just direct, and it's mathematically consistent. In alpha can be anything. So in 2 dimensions, it's mathematically consistent. Now, if it's a non-abelian anion, so this alpha has this, it depends, it's how many times you braid around it. So actually I should write here alpha n, whereas the number of times you braid around it. Now it forms a representation of the braid group. In a non-abelian representation, you have, say, 2 or 3 states. The particle will have some internal degree of freedom. Apart from position, there will be some 2 or 3 states. And this will generalize to again, if I label it by where n represents the braiding operation. So that's why this acts like a gate. You have one anion in one particle in one state, the other particle in another state. You do a braiding thing and you get to a new state, depending on more complicated than that, but roughly that. Sorry? Yes, so those are parastatistics. So those I'm not discussing. These are the braid group representations which have got physically realized, and that's why the focus is on them. Huh? Yes. Yes, yes. By one of the configuration space is the braid group only in 2 dimensions. So now these have also been experimentally realized using Josephson junction circuits as a qubit, I think, in this particular experiment. Okay, so now let me come to what work that has been done in MathScience. So as far as I know, the first paper on anions was by Murthy and collaborators. Actually, he was probably in visiting McMaster at that time because MathScience name was kept on over here. But this was 91. semi-classical physics of quantum mechanics of anyons. After this, there have been a lot of papers on quantum mechanics of anyons in general. Dape, Murthy, Dape, then finally Radhika Vatson's PhD thesis was based on this work. Anion quantum mechanics, semi-classical, and not only quantum mechanics, classical, I mean in the sense, like, this is a very interesting thing that it's a non-interacting particle, but it's not a general integrable system. Now, I don't know more about it, Murthy Jataya here if questions come. Pseudo-integrable system. Then A.K. Mishra and G. Rajshekharan. So they have written a paper, this is, I mean, I put this here to compare the dates. 1991, same time as Haldane's paper, and also saying, I mean, with a new exclusion principle. So at that time, I guess, Mishra ji had not joined math science yet, he is still in Karakuri. So of course the concept was different from Haldane, and the systems they had in mind, physical systems they had in mind were different also. I think they were motivated more by this large U limit of the Hubbard model, where there are a lot of constraints coming from the repulsion, and that can modify your algebra of creative annihilation operators. And that's the line they went on. So actually they've done there have been a lot of papers by A.K. Mishra and Rajshekharan from math science on going ahead with this algebra approach and having different statistics. So then this is the thing where we sort of computed the exclusion statistics of anion. Now with hindsight, we didn't write the paper in this spirit, but I guess what we are asking here is that suppose there are particles satisfying Hartree condition, that is, they cannot sit at the same point. Does it necessarily mean that it satisfies Pauli exclusion principle? Naively it would seem so. But if two particles cannot sit at the same point, then they cannot sit in the same state. But surprisingly it is not true, and what they show is that for anion gas, it actually obeys fractional statistics. So I won't go into the methodology, but how the second virial coefficient comes in, etc., that's technical. But so the results we have was that for anion gas, so G is the exclusion statistics parameter and alpha is the exchange phase. G and alpha have related this way. So for alpha equal to 0 for bosons, G is also 0. And for alpha equal to 1, that is fermions, G is equal to 1. And then you can have an interpolation between boson and fermion. Then for a FQHE system, that is systems confined to a particular Landau level, we got G equal to alpha, which is consistent with Haldane's result. Then 1D spin-on, actually we discussed the case of 1D Luttinger liquid, that is a C equal to 1 conformal field theory, and looked at and showed there that the G was equal to the radius of the theory. So for the spin-on case, it comes down to G equal to half, which is consistent with Haldane's result. Then we had looked at this, what do you call it? Calogero-Sutherland model. The Calogero-Sutherland model is this model of one-dimensional particles interacting via 1 by r square interaction. It's an exactly solvable model and has a user-friendly solution. wave functions can be written down, spectrum can be computed, totally solvable. I see.
Both are independently. It's okay.
Yeah. Yeah, okay. And again, let me not go through the details, but what we proved in that paper using the exact solution was that, you can calculate the, what do you call it, equivalent of the Bose distribution. So there's a distribution called Wu distribution, Wu had derived for fractionally, for the Haldane proper particles. And we showed that the Calagios-Sullivan model satisfied this Wu distribution. There are some technical issues with the distribution which I'm not going to go into here. Then the full partition function can be written in a factorized form, just like in ideal gas. And also finally, the visual expansion can be done exactly, and only the second visual quotient contains information about the statistics. So basically this gives, we've shown that this gives you a nice model of ideal exclusion gas in one dimension. Then this is a paper by Murthy and Rajat Baburi, which actually applies it to a physical situation. So in cold atoms, so cold fermionic atoms, you can tune the interaction strength. So you can go continuously from weak coupling to very strong coupling. So interest in this comes because of weak coupling, it's like BCS theory superconductivity. At strong coupling, it's more like condensed boson pairs. Strongly bound pairs and condensed. Now the intermediate point is called the unitarity point. And what they showed that if you analyze this energy density here, assuming that these particles are having a Wu distribution, then the answer matches pretty well with Monte Carlo studies of the same system. So here is one possible physical realization of these properties. Now we'll come to the spin liquid part, ITC the same. So this was the paper, the Kitay model was that a paper that I had shown earlier, where we had given a frustrated antiferromagnet which was exactly solvable and showed the existence of spin-on effect. So we had got some exact results for this, that which showed that it was a spin liquid indeed in terms of spin-spin. Spin liquid definition means that spin-spin correlation functions should die off exponentially. There's no long range order in it, and they should. So here, of course, it does that, but it also does it in a very peculiar way. And that is what we brought out in this paper. And of course, so then with this experience, Kitay model was, that model that the original Kitay wrote was on a hexagonal lattice. But you can generalize it to large number. It's actually a huge class of models which have a same solution or which are exactly solved in the same way. So with that experience, we went on trying to fool around with other simpler models and wrote this paper manipulating unpaired matter. So this significance of an unpaired Majorana fermion is that it is the thing that forms a non-abelian qubit. So actually, it's like Majorana fermion means just a real operator, But basically two unpaired Majoran fermions which are far away from each other can get coupled and form the qubit, which is the non-abelian qubit. So now you need to, in order to make gates, etc., you need to manipulate these. You have to be able to move them around. So in this paper we showed, we took a simple model, which is of, here this is what we call tetrahedral model, this is a Hamiltonian, and so that you can tune the coupling, so that this unpaired, you tune the flux, some couplings of these things, which if there's unpaired one here, you can move it here to here to here to here. You can move it up and down this chain by suitably tuning couplings. So this was from the thesis of Abhinav Saket. So there we had discovered a much simpler model later, where the same thing could be done. That is this one. And again, I won't go into the details, but here again you can, by changing the strength of these couplings, you can move the unpaired spin from here to here to here. And by the way, so the qubit here will be the when there's unpaired spin here and unpaired spin here at the edges. And the degeneracy will die down exponentially with the length of this chain. So that also it's not, so the one guy here, they can actually sort of couple talk to each other, break the degeneracy. But that is down exponentially with the size of the chain. So Abhinav had also, you could realize these theta model in terms of Josephson junction circuits. So he had also, made a circuit which realizes this. So what unfortunately, so we could move this thing up and down the chain. What unfortunately we did not do was break them. So we have given the theory of design of a qubit, but not of a gate, which is of course very important. So that's what we should have done, but we didn't do. So I think that's all I have to say. Thank you for watching.
Okay, a wonderful talk of various things that have been done in this institute. Now, people can ask questions. Yes.
For the topological qubit, have you shown robustness against noise?
No. Couple it to external path and show it.
Yes.
No, we have not shown it explicitly. But the nature of it, because that qubit, it's a combination of states operators throughout the chain. Loosely we say that it is one operator sitting here, one operator sitting here, and then take linear combinations and form the complex fermion operator. But what that really means is that it's sitting throughout, so it's unlikely that local perturbations can have a big effect on those. So, but we have not done an explicit calculation.
This is not a question, comment. There was one Professor Ramanathan in Delhi University who independently proposed the idea of Haldane in 1992. 1991 was Haldane's paper, 1992 was Ramanathan's paper, and unfortunately that paper was published in PhysRev.D because he did it in the context of high energy physics. Fractional statistics in the context of high energy physics. Because it was in Physical Review D, none of us saw it.
And I remember when we were doing the work, he visited, somehow he didn't mention. In around 95 or so, Ramesh Kaul saw it, and then he said that, look, Haldane's idea is here. I think one should start referring to Ramanathan. Yeah, unfortunately we didn't know, we didn't refer to it. He should have been credited along with Haldane with discovery of, fractional exclusion statistics. And there was one more bit I want to add is that it's now called FES, fractional exclusion statistics, as opposed to exchange statistics.
Okay.
I think that name was used by Shankar and me in our first paper. And then it stuck to the field and it's now called fractional exclusion statistics.
Yeah, so here, this is the first time the name is being used.
Okay, since you made the comment, I'm going to make this Tagore idea was known to Feynman in his formulation of infinite product of Hilbert spaces, where he constructs Feynman algebra, and in the limit of the number of Hilbert spaces going from n to n plus 1, in that ratio of the dimension of the Hilbert spaces, exactly similar thing happens, which is called index of the subfactor. Is related to this. That's one thing. Secondly, this statistics being different in 2 plus 1 dimensional quantity theory. You remember we have also done in 1987 in nonlinear sigma model, where we found semyon, where theta is pi by 2, which is also, and we also mentioned non-abelian, but we were hesitant to mention it very strongly. So we have to keep quiet about it. That's the comment. Yeah, that's true. But we did mention semyon. We could have mentioned non-abelian also.
We have done this O3 sigma model
On a
with
torus.
periodic boundary condition. On a torus. With the topological.
Topological. Yeah.
So that group, according to us, was non-abelian.
Yes, it is. It is non-abelian.
So that gives they gave a lot of constraints on the types of statistics possible.
Okay, no, that's only minor comment. Anything else? Yes, Shyam.
This is more a comment on your comment about question rather. Qubit and qubit being superposable or not, right? That was what you are. So I will give one argument. The superposition, the super selection rule talks about you can't have direct sum of Hilbert space of fermions and bosons. Direct sum you cannot have. It doesn't say about tensor product, which is what you do with qubits and qubits. And if it is half plus tensor 1, then the decomposition is half plus 4, both of which are fermions. They can be superposed, so there is no contradiction.
Oh, yeah, that's right. Because,
Yeah.
for example,
Direct product is
we can have a state in which there is
Some
an
of
electron and a boson. There will be one electron and a boson, there will be a direct product. There is no problem there. It's the sums which are.
Can you comment on, is there anything like a non-abelian exclusion statistics? In the Haldane picture,
Okay, so let me put your question the other way. What is the Haldane statistics of non-abelian? I don't know.
I have a short. Shankar, can you go to your last transparency, mountain and beautiful moon?
That is, thank you.
Yeah. What is it and where were you there?
So yeah, this is the Nilkant mountain seen from last unusual angle. So we were on the glacier beside from where this photo was taken. So I was fast asleep inside the tent. Then our project assistant came in, woke me up and said, "Sir, you have to see this." I was unwilling. It's cold outside. Went out and entranced for this. So that project assistant, Surendra Singh Barwal, he's the guy who took this
interested.
Anything quantum about it, Shankar?
No, nothing quantum. It's a thank you, sir.
Okay. Anything else? Others? Should we close? Okay, we will go for